announcements. John, would you like to introduce our speaker tonight?
Sure thing. Gage, I'll go ahead and start the introduction if you want to go ahead and start screen sharing while I'm doing that. So everybody, I'd like to introduce Gage Siebert. Gage is a little bit of a departure from our normal invited speaker, just in that Gage is a little bit younger. I mean, we frequently have UW students talk, but generally they're doctoral students and frequently postdocs. Gage just finished his undergraduate degree at UW Madison and was quite involved in astronomy research while he was an undergraduate. And I've invited him to talk both about a little bit about himself and about the research that he was able to do as a UW undergrad. Gage is going to be matriculating this fall at the University of Arizona. Oh, I'm sorry, Arizona State University. Wrong city, Gage. Sorry about that. And he'll also, fill us in a little bit about what his plans are for the future. So everybody, give a warm MAS welcome to Gage Siebert.
Right. Thanks, John. Nice introduction. So like you said, I'm recently graduated here and moving on to ASU. And it's my pleasure to talk to you today about probably the biggest project I've worked on in my past few years, which is Tianlai. So this is an experiment. It's pictured in the background here. In particular, I'll be talking about those dishes on the left there. But another very important, I guess, research experience I've had that is probably of interest to you guys as well is that I got to do an internship at the Arecibo Observatory before it collapsed a few years ago. And that was really a very fantastic experience. And I was very lucky to do that. So I did some pulsar work there, but that won't be what I'm talking about today. And as for what I'm going to be doing in ASU, it's a bit too early to say, but I'm happy to take any questions, and so feel free to interrupt me at any point throughout the talk. But with that, I'll just begin. So this experiment Tianlai, it's a dish array. So there's 16 dishes. They're, I think, about 4 meters across, and it's in northwest China. It's in a very radio quiet area. There's a very remarkably low interference there, and it's a cosmology experiment. So cosmology is the study of like large scale structure and evolution of the universe. And Tianlai in particular is looking to improve measurements on the expansion of the universe and indirectly learn something about dark energy. So the universe has always been expanding as far as we can tell. And the energy that it would take to drive that expansion, we've been just calling dark energy. We don't really know what it is, but in learning more about how that expansion is happening, we can learn more about dark energy. And this is kind of the ultimate goal of Tianlai and other experiments like Tianlai. So I'll hopefully be able to lay out the case of why this is, something we can do with these radio experiments. So a couple important background information pieces first. And one is that hydrogen emits radio light, and this is all basically that Tianlai looks at. And all we look for, we unfortunately detect some other things, but all we're looking for is this one frequency of light that hydrogen emits, and it's called a spin flip transition. So this is a diagram of the transition here. So on the top, this is supposed to be like a neutral hydrogen atom. So in the middle, you have a nucleus of your hydrogen atom, so it's just a proton. And on the outside, you have an electron. And these arrows indicate the magnetic fields of them. So much like a normal magnet that we're accustomed to in our macroscopic lives, they have a north pole. And so these arrows are just indicating where the north poles are pointing. So in the top picture, they're pointing in the same direction, but in the bottom picture, they're pointing in the opposite direction. And much like normal macroscopic magnets, if you put two of them next to one another, they like to put their north poles next to their partner's south poles. It's a little bit of a lower energy state, and the same is true inside the hydrogen atom. And so if a hydrogen atom starts in the top case where both spins are aligned, as approximately half of them do in the early days of the universe, then give it enough time that the spin of the electron will flip. And because it's moving to a lower energy state and that energy has to be conserved, it emits that energy in a photon. And so or a particle of light. And that energy that's in that particle uniquely determines both the frequency and the wavelength of that light. And so the frequency ends up being 1420 megahertz, and the wavelength is about 21 centimeters. And so this puts it firmly in the radio regime. And so this is really the core physical process that we're observing when we use Tianlai. And so another important concept is redshift. So we can think about this 21 centimeter emission coming from hydrogen from long, long ago. And when it was emitted as 21 centimeters, but by the time it gets to us, we might not observe it to be that. We might observe it to be 30 centimeters. And the process causing this is a redshift. So this is when light moving in an expanding universe expands with time. And a nice, similar example to see is to imagine if you were to draw this wave on a balloon and then blow up the balloon. So that's a lot like the way in which the universe is expanding. So it's not that the light is getting moved to a different direction because of this expansion, but the space that the wave is embedded in is expanding. And so in this case, it's the plastic or rubber, whatever a balloon is made of. The material of the wave is drawn on is what's expanding, and so that expands the wave. And so blue light is the shortest visible light that we can see, and red is the longest wavelength light. And so this redshift moves things towards the red, and that's why it gets its name. So this picture here is a timeline of the universe, and all the terms aren't super important, but in terms of, I think it's a really nice picture. So on the left, we have the earliest days, and on the right, we have the present day. And so maybe I'll walk us back in time. So I'll start here where we're in the present day, and there's a few galaxies sparsely spread out, and we happen to be in one of those. But as we move farther back in time, those galaxies are less dense, and there's actually more galaxies, and they're lighter. So over time, these galaxies have been combining and condensing down. But as we go back in time, the matter is getting kind of spread out more evenly around space, and the gravity had been collapsing it. And eventually we move so far back in this region called, or I guess right after reionization, where there's not even galaxies formed yet. So it's just loose gas that's starting to collapse. And at some point, there were the first stars that were forming, and this is what we call cosmic dawn. So before this, it was just what we call the dark ages, which was primarily just neutral hydrogen everywhere. And there was no real active sources of light and no real interesting chemistry happening yet. The universe was almost entirely just hydrogen at this point. And before that, we get to the really cosmologically interesting times. So this is the cosmic microwave background, or the CMB. So this is this blue and red disk here at the back. And then before that, for about the first 300,000 years of the universe was just one hot, dense plasma. And so that means it was still primarily just hydrogen, because that's what the universe started out as, but it was all ionized. So anytime an electron would combine with an atom, there was high enough energy light readily available to knock that electron right off. And so it ended up being the case that there really wasn't any substantial amount of neutral hydrogen to speak of, and it was just a big plasma everywhere. And this plasma behaved a lot like a fluid in that it had a pressure, and you could propagate waves in it. And it was like air in the case that pressure and temperature actually went with one another. So when you had higher pressure areas, you have higher temperature. But eventually the day of the plasma came to an end, and the CMB was created. So the CMB is this rather famous picture here. So this is the cosmic microwave background. So this is the epoch that marks the end of the universe as one big plasma ball. And what happened was, as the universe was expanding and cooling, one day almost overnight, in terms of cosmic timescales, the universe cooled enough for the hydrogen to actually remain neutral. And so and that's because as the universe is expanding, you could think about that light that was there and readily able to knock off those electrons. Well, eventually it got so redshifted that it could no longer do that. It didn't have enough energy to do that anymore. And so when that happened, all of that light that was around that just no longer interacted with the hydrogen. We say they got decoupled. And so we can look around in all different directions and see this cosmic microwave background. And this is actually a map of that. So these different colors here indicate heat. It's a heat map. So the orange to reddish spots are more hot. So that means that the plasma at that part of the universe where we're looking, excuse me, was hotter and denser. And in the blue parts, it was an underdensity. In particular, this underdensity in the central bottom left or bottom right quadrant, I guess. This very big underdensity. And so this kind of picture looks a bit random, but there are many, non-intuitive tests we can do on this to see if this is truly random. And this is of great interest because this is as far back as we can see. It's, people call it the edge of the observable universe because as you look further and further back, you can't look past this, right? It's opaque. And no matter what wavelength you care about, you can't see anything beyond this. And so if there's any thing we're interested in that happened in the very early universe, this is about as close as we can get experimentally to looking at it. And so one question people might have is about how, homogeneous or how uniformly distributed was all of the matter in those early days. And we can actually learn a lot from that by looking at the cosmic microwave background. And so one test we might imagine doing is we might say, pick some random point on this map here and look at all the points 1 degree away from it and just form some number based on how much they have in common. So for example, I'll look at a cold spot and I'll say, how likely is it that if the spot I'm looking at is a cold spot, that the spots with 1 degree of angular separation from that cold spot, how likely is it that those spots are also cold? Or how likely is it that they're hot? And you can compute these kinds of things for every single point on the map very quickly with a substantially strong enough computer. And when you do that, you get a very interesting graph. So this graph here, the angular scale I'm talking about, this is doing that same kind of operation I was trying to describe just a moment ago. And so this angular scale is varying. This is small angular scales where the separation is very small and up to large fractions of the whole sky, so 90-degree separations. So this vertical axis is basically like a strength of correlation. And so what you should read from this graph is that the points 1 degree separated from one another are highly correlated, as are not the same degree, but also points at about 0.5 degree and 0.2 degrees. And the phenomena that produces this are called Baryonic acoustic oscillations, or BAOs. That's a really jargony term, but the first part is just talking about baryons, which is a kind of catch-all term for all kinds of normal matter. So it's just, it's what we're made of, and everything we interact with on Earth, all the physical objects are baryons. And then these acoustic oscillations, they're called that because the waves that produce these are a lot like sound waves. So these are waves in the early universe that were acting like density waves, much like sound waves are. So, right, if the way you hear me is that there's some membrane in your computer or your phone, depending on how you're listening, and that's being driven back and forth by a magnet. And it's compressing air and making a little vacuum, compressing air again. And so those are acoustic oscillations that are reaching your ear. And similar phenomena were happening in the early universe before the CMB. So the it's really interesting exactly how these come about. So we can imagine the start of the story is we have some really hot, extremely dense plasma laid out, but it's not perfectly smooth. There's not perfectly evenly distributed. There are some spots that are a little bit more dense, and there's some spots that are just a little bit less dense. Not crazy, not by a factor of 2 or anything, but just a little. And those spots that are, say, a little bit more dense when they start out, we can imagine that that's maybe this red spot here for an instant in time. If it's a little bit more dense than everywhere else around it, it has a bit more gravity. So it can pull in some of the matter and some of the plasma around it and get a little bit more dense. But this plasma behaves a lot like a gas. And when it gets pushed into a tiny little area, it builds up a lot of pressure. And that pressure grows fast enough to actually overcome that gravity. And so you get an oscillatory force. It pushes back out and it can come back in. And so you get these kinds of oscillations driven inward by gravity and outward by the pressure of the plasma. And so these are what we're actually observing when we look at the CMB and we see these kinds of correlations here. So on to the next, yes, excellent. Okay, so these BAO features, as we'll call them, or just they're kind of spatial correlations on different scales. We observe these on the CMB, but I want to make the case that it's actually still relevant to us later on in the universe. And so, you know, before in this kind of white region in the back of the plot here, it's a plasma and these things are propagating like waves in a fluid. But right when the CMB is released, the universe stops behaving like one big fluid. Those atoms needed the light to mediate the forces between them. And when they're neutral atoms, they hardly interact at all. And gravity becomes like the dominant force. And so these waves that we're propagating, it was like you disturb the surface of a body of water, a lake or something, and then you just almost instantaneously froze it. And so all those perturbations to the distribution of matter get frozen in time. And of course, the universe then evolves and those expand because the universe is expanding, but they're not being driven outward by the same force that was creating them pre-CMB. And so the scale of these waves is actually much larger than a single galaxy. And this is where we kind of get into the line intensity mapping. So the line intensity mapping, we're looking at the distribution of many, many galaxies at a later point in the universe. And so this is kind of a nice diagram of it here. So suppose we're looking at this slice of the universe. So we're over here looking back in time. And this image in the top right is what we see. And it's kind of like a heat map. So we're not actually resolving individual galaxies. You can see on that plot in the center right, those individual galaxies are the gray dots. And we don't actually care where any individual galaxy is. We just care about the large scale distribution of thousands and hundreds of thousands of galaxies in aggregate. And we care about how those are distributed with respect to one another. And the reason we do that is because we can look at that little map like you see in the top right there, and we can do the same kind of procedure that we did on the CMB, where I pick a hot spot, or in this case, a hydrogen dense area, which is really just a proxy for all matter. But we pick a hot spot and we ask, okay, at some separation, how likely is it that there's other hotspots around? And we can kind of compute this in just the same way that we did for the CMB. And so just as we have these kinds of peaks for the CMB, we'll get these later on at any different redshift we want. And now this is where redshift plays a kind of important role too. So I talked about earlier that the hydrogen always emits radiation at 1428 megahertz or 1420 megahertz. And of course, that's true if you're a nearby hydrogen. But if we're looking at hydrogen from, say, the cosmic dawn or reionization, some really far distant past, it's been redshifted by a huge amount by the time it reaches us. And so maybe it was emitted as 21 centimeters, but by the time we see it, it's 30 or 40 or what have you. And so in this way, if we know that what we're looking at is light that was emitted from hydrogen, then we can just be very careful about measuring exactly what frequency we observe that light to be. And in so doing, we determine at what redshift we have observe this hydrogen at. And so we can kind of make these slices in time. And so I should say that this redshift, it's measured in a quantity called Z, and it kind of goes in a non-intuitive way. So you'd think it started 0 at the beginning of the universe and go to some higher number by the time it reaches us, but we actually start at 0 because, you know, anthropocentrism and whatnot. And so as we go farther back in time, we say we're looking at higher and higher redshift. So from our perspective, these sources are at higher redshift. So that's a big picture of how the I guess just to recap, to make sure, yeah, to bring it home, is that we're going to make a similar plot, or experiments hope to make a similar plot to this one in the bottom left here. They're called BAO wiggles. We hope to make a similar plot like this by measuring many different galaxies, the hydrogen from many different galaxies in the later universe. And then we're going to compare the sizes of these with these really precise measurements that we have of the CMB and these features in the CMB. And from that, we can learn about how much from the time of the CMB to whenever it is we measure these galaxies, we can learn how much the universe has expanded by how much these features have grown, because we know that the waves aren't propagating these features anymore. And so any change that happens in size between the CMB and later universe is solely due to the expansion of the universe. And so in this way, we can get very sensitive measurements to the expansion of the universe over time. And that further informs us about dark energy, helps us parameterize it at least, if nothing else. So to understand a bit more about how Tianlai actually does this as like a physical instrument, what it's doing, we have to talk a little bit more about waves. So I'm using the same GIF again, but I'm going to kind of abuse it and use it in a rather different context, which is that, you know, imagine this red dot at the center is some kind of star, and that star is emitting light. If you were watching from some crazy perspective where you can watch light move, you would see the light emanating from this object in these spheres that just grow, and they're centered on that object. And we're very familiar with large spheres, like the Earth, for example. So when we look out on the horizon of a sufficiently large lake or an ocean, we see a flat surface, like we see at the top of the screen here. It looks very flat. And so that's a really good approximation. As your circle gets bigger and bigger, approximating the surface of it as flat becomes very excellent, especially when the size of the circle is the distance between, say, some other star and Earth. It's an excellent approximation that gets used all the time in astronomy and is kind of the backbone behind why experiments like Tianlai work. So one other important property of waves that we need is interference. So there's constructive and destructive interference. And this is a nice GIF, I think, that demonstrates that. So these two waves on top, these a bit thinner, they're being added together vertically. So I'm just taking a line, cutting straight down, and I'm adding up the heights of those 2 points and producing this bottom wave, this darker one at the bottom. So you can see for these two waves, when the peaks line up with the peaks, as is happening right about now, this bottom wave is as high as it ever gets. But then once these peaks line up with its component or its partner's trough or the low spot, this bottom wave becomes flat. So the constructive interference is when the peaks match the peaks and they get as high as they ever do. And the destructive interference is when they cancel out completely and it's just a flat wave on the bottom. So using these two things, we can talk a little bit about what interferometry is. So there's a bunch of symbols in here, but I just like the cartoon. The symbols aren't important. So this is kind of a cartoon of what we're doing with an experiment like Tianlai. So these are two dishes for Tianlai, it doesn't matter which ones. And they're looking in the direction of these dotted lines. So there's some star up and to the right, or whatever it is we're looking at, it's up and to the right. And so the light coming to us from that star is coming in big spherical shells, like the GIF from a couple slides ago. And by the time it's reaching Tianlai, the surface of that shell looks like this line right here. It's cutting across its perpendicular to the direction it's moving in, which is that dotted line. And something we can immediately see is that the signals coming from our source, they reach dish number 2 before they reach dish number 1, because light has to travel this extra distance. This right there, I hope you can see my cursor. And so this is something we can make very good use of to actually get really good data. And so the way we can do that is by utilizing the properties of constructive and destructive interference with these waves. So if we measure very carefully where these different antennae are, and we know where we're pointing them, then we know that the signal's getting here, X seconds before this one. And we also know that the signal comes in to our antenna and it becomes a signal in a wire, and those signals propagate in wires with some finite speed too. So we can just make the wire coming from dish 2 a little bit longer. So that's kind of depicted by this little loop here, this tau 0 loop here. We're making the signal or the wire a little bit longer from dish 2. And what we're doing is we're matching the time for this. So this, whatever this distance is here on this tau 0, it's offsetting the time it takes for the light to travel to the dish 1. And so when we bring these two signals together down in the center here and we multiply them, they're reaching each other at the same time. The signals are matching up from our source that we want to look at. And so what this does is that it squares or constructively interferes our signal, but all of the random noise that comes in the radio antennas, which there is no shortage of, that stuff is really unrelated antenna to antenna largely. And so it on average tends to cancel out or sometimes even destructively interfere. And so it's in this way that we can take two antennas, observe something, and get a signal that's more than the sum of the parts. We can multiply those voltages together, the signals together in a very careful way and get a lot more signal than we would from just using either dish on their own. And so this pair of antennas that we're using here is called the baseline. And Tianlai has 16 dishes, each with 2 antennas. And so we have 32 antennas, and we compute a baseline between each of those 32 antennas. So that comes out to 528 pairs, and 528 baselines. So there's a lot of electronics that goes on into here. I don't know what the number is, but I'm sure miles of fiber optic cables and whatnot. And we're also have frequency resolution. And so you can kind of think of that as like resolving different colors. So like maybe our camera is really bad and it only has R, G, and B, in which case we have 3 frequency channels. Well, Tianlai is a lot more sensitive to that. So we have 512 frequency channels. So it's like we have not just R, G, and B, but hundreds of different shades of R and hundreds of different shades of G and whatnot. And so we take all of those, and each of these baselines makes a measurement every second. And so that comes out to about 300,000 measurements a second, a little bit less. So this very quickly turns into a big data problem because we are producing terabytes of data from this array. But there's other challenges too. So if we were to take Tianlai and make a map of the whole sky, it would look something like this picture that I have here. So this is a simulation that I've computed, and this is what Tianlai would see if we were to map the whole sky. And what we would expect, and what is kind of a real bedrock assumption of cosmology, is that the universe is kind of the same in all directions. There's not one favored direction. But if I'd ask you if this passes that test, the answer would be it doesn't, because there's clearly some spot in here that's special, and it's the center of it, or this whole center line here. So what we're actually seeing here is not the cosmological neutral hydrogen distribution, but we're actually seeing foregrounds, galactic foregrounds. So this is the galaxy, right? So we're in the plane, in the galactic plane. So this is like the Milky Way, which you see across the sky, and the center being here. And these foregrounds are tens of thousands of times brighter than the actual hydrogen signal we're looking for. And so it's an extremely important challenge to overcome this. It's from my understanding, I think it's one of the biggest challenges this field faces at the moment. And so there's lots of ways to come at this. So what some people do is they just don't observe in the galactic plane, which is a good start, right? So you look in these far corners that look a bit darker, but even then you still have some bright stars in there that mess you up. And so you can make a catalog of all the bright stars in our galaxy, and you can just subtract those out too. And then you're relying on the fact that you did your catalog well. But even still after that, there's some diffuse local dust that is going to mess you up. So there's charged dust and large magnetic fields stretching through the whole galaxy that create a little bit of radio radiation. And that stuff is still, just because it's so close, just overwhelms our hydrogen signal. And so there's lots of very sophisticated statistical methods, and some people are using machine learning and neural networks to try to overcome these things, but it's very much so an active field in this. And another thing that's, I think, special about Tianlai is that we actually had to, or we didn't have to, we chose to observe the same point in the sky for a very long period of time. So we have actually over 5,000 hours of observations on a single pointing, which is the North Pole. So the North Celestial Pole, we just pointed the telescopes there, and it had the advantage that we didn't have to move the telescopes. So yeah, we just pointed them at the North Pole and took data for the better part of a year and a half. And it's just a really unique data set, and these things are still in the works. And I think this is the kind of the end of the cosmology section of the talk. So if you have questions about that, feel free to chime in, but I'm going to pivot now to some more astrophysical, I guess, purposes or uses that this Tianlai data set can be used for, at least that I'm hoping to use it for. So in particular, this data, we observed, like I said, 5,000 hours plus on one pointing, the North Celestial Pole. And that's really special. So most telescopes, if they are these really big ones, they don't spend more than a few hours on any given pointing. So the data we have is really unique in that sense, but I wanted to, get something out of that. And what I realized was that if you're looking for something that repeats or is, periodic, your sensitivity to that grows with observation time. And it grows with like the square root of time. So it grows really fast at first. There's kind of diminishing returns as you go on. But in principle, if you observe for an arbitrarily large amount of time, you will reach arbitrarily large sensitivities. And so this GIF here is kind of displaying that. So this is a simulation I've made of some weak sinusoidal signal buried underneath some noise. And we're observing it with Tianlai. And so the first few frames of the GIF, you can tell it's extremely noisy. You can hardly tell there's a sinusoid in there at all. By the end of the GIF, it hardly looks like it's even changing at all. And so, yeah, there was just the beginning again. It's getting more and more smooth. And if we let this GIF run on for however long we like, that sine curve will get as smooth as we like. And that's because the noise is uncorrelated, or meaning it's unrandom, it's random. And so when we so I'm just taking really long sets of data and I'm breaking them into, you can see on the bottom axis here, 2-minute chunks, so 120 seconds. And I'm just averaging them on top of one another. And so as I average more and more of those, the sine signal, this wave, down and then up, that's the same in every single one. And even though it's much larger, the noise is not the same in every single one. And so on average, it averages down to 0. And so we just take larger and larger averages, and that average gets closer and closer to 0. And so this is kind of the core motivation for this project that I'm doing, which is searching for periodic sources with our data. And there's a bit more of it's a bit more well motivated than that. So there are already some very sophisticated algorithms that have been made to do these kinds of searches. And so these have been done for pulsar searches. So these are looking at pulsars, which are neutron stars. They spin around really fast and have very strong magnetic fields. And so they look a lot like this picture here, in that they're like cosmic lighthouses, right? So they have these strong polar magnetic fields that are giving out really strong radiation, in particular in radio. And because they're spinning around so fast, we get this kind of periodic blip when they happen to be pointing at Earth. They look like they're on. And those tend to spin with periods of a second down to like a few milliseconds. And so pulsar searches already exist. These are kinds of things that have already been done, but they don't observe for more than a few minutes at a time in any part of the sky. But to get to other kinds of periodic sources with periods of minutes or hours, there aren't really good data sets for that. And no one's ever even really tried to do that. Now, if we were being pessimistic, we might think, well, maybe that's because nothing like that exists. But actually, there are some sources that exist like this. And there's actually a white dwarf pulsar, so it's called AR Scorpii. I recommend checking out. It's very interesting in its own right. So this has it's a very extreme case, but this white dwarf beams out radiation much like a pulsar does, which are typically neutron stars. But it has a period of, I think, 2 to 3 minutes, somewhere in that regime. And there's also brown dwarfs and even sufficiently large exoplanets who can have radio flares that are periodic with periods of about hours. And the kinds of mechanisms that are driving these are quite similar to pulsars in the sense that they're all driven by these polar magnetic fields, and the periodic nature comes from the rotational period of these bodies. So it's like how this is actually a picture of Jupiter with aurora on the right here. And these aurora, just like the ones on Earth, are actually very radio loud. In addition to producing visible light that we get to see and enjoy, there's a great deal of radio light that gets emitted by them too. And so when some of these planets rotate around and their aurora become periodically visible or unvisible from us, then we can see a periodic source there. And so Tianlai is really one of the first, I think Tianlai this is the first experiment that is applying these kinds of search methods to things with much slower periods. And I made sure to find these things and talk about these things when I'm presenting them, because it's important that, it's well motivated and there are objects that have these kinds of periods that already exist. But for me personally, like, this isn't what I find most exciting about this. So I'm, very excited about this project, but it's actually for other reasons, which is that I think it's a pretty good search for extraterrestrial intelligence. And so I'm hoping to make that case to you here. So this is, I'll speak in analogy to Earth. So suppose we're looking at Earth from far away, and really the only assumption I think you need to make for this to be a plausible argument is that a different technologically capable species might have satellites in orbit that use radio. Need not even be for communication. It could be for imaging. It could be for whatever. But if those satellites produce radio emission, I think in principle, this is the kind of experiment that can detect them. And so I'll dive into the example here. So as we're looking at Earth from far away, all these white dots are actually, this is a map of, at some point in time, of all the known human-made satellites. And maybe one of the first things that jumps out is that there's a high density of them very close to the surface of Earth. And so these satellites, many of them are beaming radio light down and getting radio beamed up at them. And this is something that in principle we can detect from far away because it's radio light and we have radio telescopes. But it's probably really weak, and we kind of would wish it would be periodic, because then we can use this trick that I was talking about earlier where we can just keep stacking on different versions of it and get to arbitrarily high sensitivity. And we actually can get that in this case because these low satellites, they are periodically invisible to us, meaning that, like, if this is the planet they are visible, and then they go behind the planet and they're not invisible, or they're not visible, excuse me. And so, in Earth's case, if we were to look at Earth, we would expect these satellites, the signal from the bulk of these satellites, to have a period of about 90 minutes, because that's how long a low Earth orbit takes, is 90 minutes. And so you could detect satellites with periods of that, but none less. You could detect some more, perhaps, but the preponderance of them exists at about a period of 90 minutes. And so that's where you're most sensitive to detect them, at least around Earth. And so around some other hypothetical planet, it might be some other period of time that corresponds to their low planetary orbit. Doing this has a lot of unique data analysis challenges with it, but one really interesting example that I think is kind of fun relies on two fairly common fun space facts. So one is that it takes about 8 minutes for light from the sun to reach Earth. And another is that the Earth is tilted with respect to its orbital plane by about 23 degrees. And so these are, at the outset, the two things we need to know to do this brief calculation. I said I would do no math, but I think this is really fun, so I lied. So the distance between Earth and Sun in light travel times in this little diagram. So this is Earth in December, where you can see it's winter in the Northern Hemisphere, right? We're pointed away from the sun. This is the spin axis. And Earth in June over here. So I guess Earth now. This is about 16 minutes in light travel time. And the thing we're actually going to try to calculate is a delay similar to how there's that delay in interferometers between the two dishes. So like if this over on the left, Earth in June was dish 1 and Earth in December was dish 2, and we're looking up at the North Celestial Pole, right? So we're looking actually at these arrows that denote our spin axes. And so we're looking up in this direction, and light is moving down here, and it actually has to go this distance A over on the left. Light has to travel that extra distance to reach us in June versus in December. So in December, Earth is closer to all these sources in the direction of the North Celestial Pole than it is in June. And it's not the end of the world, but for the kinds of search algorithms I want to use to look for periodic signals in this data, it actually is a really big problem. It's important that, if I look 6 months in the future, that wave is right where I expect it to be. And that's because I'm averaging, say, in the case of that GIF I showed at the beginning, I'm cutting up my data into 120-second little bits. And if that starts to drift off, then the signal doesn't average with itself anymore. It starts to cancel out. And so it's really important that we get this right. And so just to see, what the magnitude of this effect is, we can set up a triangle between Earth in December, Earth in June, and this imaginary point here that denotes where the light has to travel an extra distance to reach Earth in June. So we know that this is the hypotenuse. This is 16 minutes of light travel time. And we know that this angle here is 23.4 degrees, because that's how far the Earth is tilted off of its orbital axis. And then we can do some trigs. This is SOHCAHTOA. I still have to say that every time. So the sine of this angle, SO opposite over hypotenuse. The sine of this angle is going to be A over C. We multiply by, or C over A. We multiply by A on both sides, right? And then we get that this distance in light travel time is going to be about 6.5 minutes.
I'd just like to point out a minor error in the diagram there.
Yeah.
The Earth is actually closer to the sun in December than it is in June.
Yes. Yeah, I guess that's another assumption I made, which is that it's circular. But for an approximate, yes, amendment accepted. Absolutely. Thank you. Yeah, so with that, I will, pause for questions. So thank you for your time and the chance to speak today. It was enjoyable.
That's kind of fun to think about these kind of techniques, because I think, I've heard recently, where they've been able to measure, stellar parallax at farther and farther distances because of using these kind of interferometry techniques with whether it's radio telescopes or optical telescopes, and is just amazing technology. And I can only imagine what kind of computing power is needed to run the kind of operation you're running in.
Yeah, that's really interesting. And one thing that I guess I didn't talk about, but it's definitely relevant here, is that for these intensity mapping things, I guess I'll go back to the diagram of the dishes. So these dishes are all pretty close packed in terms of typical interferometers. A lot of the times, there's experiments in recent years that have measured event horizons of black holes, right? And those use telescopes on all over the world. And so those baselines get really long. And so those long baselines are really good for that, getting really small angular resolution, but you kind of lose a sacrifice in accuracy. And with Tianlai, because we're doing these intensity mapping and we don't care about actually resolving individual galaxies, we put them all right next to each other to get the lowest noise in the data and to get the highest sensitivity and just a nice coarse grain topographic map.
Yeah, any more questions for Gage?
I just want to wish him very, very good luck, and I hope he's successful in his studies at Arizona, and I hope he enjoys the heat.
So do you ever get to travel to any of these different sites and things then?
I have not been to China, no.
All right, well,
Okay.
Oh, go ahead.
I just want to wish you congratulations and good luck in future endeavors.
Thank you.
Yeah, this is a really neat project and a really fun topic. And on behalf of Madison Astronomical Society, Gage, I'd really like to express our deepest gratitude for you to share your presentation with us tonight and tell us all about this. I'm having one of my moments. Telling us all about this radio telescope array. It's really neat.
Thanks for the opportunity.